Hello everyone, my name is Abdul Yusuf, a PhD student at Institut de Maintenance et de Sécurité Industrielle. Today I'm going to give a presentation about the improvement of heat transfer inside electrical machines. So the title of my presentation is Impact of the Geometrical Form and the Enhancement of Heat Transfer in the Groove Rotor of Electrical Machines. So my presentation is divided into 5 main sections. Firstly, an introduction. Secondly, the thermal behavior inside synchronous machines. Then I will explain the physical and numerical model and interpret the result of the numerical simulation. And finally, in conclusion, summarizes the work undertaken in this research. So let's begin with an introduction. Electrical motors and alternators are machines used to generate electrical or mechanical energy in many industrial applications like thermal power station and hydraulic central. So the synchronous machine consists of the rotor and stator separated by an air gap. The stator is the fixed part of the alternator and is made up of a magnetic circuit and windings, and the rotor is the rotating part. So the design of these machines is a multi-phase physics problem comprising electromagnetic, thermal and structural design. So the transformation of energy from one form to another by means of a machine is always accompanied by a heating of the different parts of the machine, and the increase in temperature can also modify the properties of the material we coat. So we coat for example permanent magnets and winding insulator. And the thermal analysis is an important subject that can affect the electrical performance of the machine. In fact, an operating temperature that is too high can lead to unnecessary power losses and affect the efficiency of the machine. For example, Joule stator losses, iron losses, and Joule rotor losses, and mechanical losses. All of these losses are responsible for the warm-ups. Therefore, to avoid exceeding critical temperature in the machine, we need an extremely efficient cooling and ventilation system capable of answering sufficient removal of the internal heat of the machine. So cooling is essential for the productivity and to protect the internal part of the machine from thermal damage. So there are several types of cooling machines, but in our study the cooling is by air circulation. In addition, one of the efficient ways to dissipate the heat generated and increase the lifetime of the stator insulation in the electrical machines is by using axial grooves. So the presence of axial grooves on stator or rotor the effective technique that's used for saving energy and increasing heat transfer of airflow inside electrical machines. So part of the rotor is formed by conductors housed in the longitudinal grooves of the rotor shaft to provide cooling. As you can see in both figures, the first figure is for grooves mounted on the rotor, and the second for grooves mounted on the stator. Now let's move on. The next topic is numerical method. So this work performed with computational fluid dynamics CFD to predict the thermal behavior inside rotating electrical machines. So the process of conducting a numerical simulation is, the first step is pre-processing by using ICM CFD for the creation of the geometry and mesh generation. Then ICM is a complete tool capable of creating complex geometry, and it allows generating a mesh for a given geometry with hexahedral and tetrahedral meshes, with the possibility of exporting a mesh file for varieties of CFD software. The second step is numerical simulation for the definition of physical problem and problem resolution, where the governing equations are solved by the use of of the ANSYS fluent solver based on the finite volume method, and this method is based on the discretization of the transport equation. So the last step is post-processing, is by using CFD post to plot the profiles of temperature, velocity and pressure. Moreover, the CFD technique has become a tool widely used for most particular applications to study the flows by the numerical resolution of the equation governing the fluids. So in this study I used the Reynolds average Navier-Stokes approach because it's the most commonly used for modeling turbulent flows, where the turbulence closure is done with the help of SST turbulence model coupled with automatic wall function strategy. And the idea behind the SST is to combine the model K epsilon and the model K omega using damping coefficient F, and the latter is equal to 1 near the wall and 0 away from the wall, and it activates the model of Wilson K omega in the region near the wall and model K epsilon for the rest of the flow. So the formulation of the SST model is as follows. So there is two equations of this model. The first equation is turbulent kinetic energy and the dissipation rate. I will pass now on the problem description. So, three-dimensional steady-state calculation of the heated rotor wall with trapezoidal grooves were performed using software called ANSYS Fluent to predict the flow and heat transfer around the grooves. So the computational domain considered in this study consists of two coaxial cylinders of length L equal 186 millimeters, and the radius of the stator and the rotor is R1 equal 190 millimeters, and the radius of stator R2 equal 129 with air gap E equal 10 millimeters. So to solve the equations, it's necessary to determine the boundary conditions. So figure 6 shows the boundary condition imposed on the fluid domain. At the inlet, a uniform axial velocity has been imposed with an ambient temperature of air, and while the radial velocity and tangential velocity equal 0, and a zero pressure gradient was taken at the excite channel. The rotor wall and trapezoidal groove are maintained at a constant temperature T rotor equal 71.6 degrees Celsius, and the rotational speed equal 52.36 radian per second. On the other hand, the top wall of stator is considered to be adiabatic and both side walls as periodical. So to simulate our fluid domain, meshing is performed by using ICM CFD to create hexahedral mesh as shown in figure 7. So the fluid domain was discretized by using a structured grid with refining the mesh. So for the same Taylor number and grooves aspect ratio, we tested three meshes, three grids. So the first grid with 400,000 nodes, and the second with 600,000 nodes, and the last grid with 800,000 nodes. And the figure shows also that all the three meshes have been similar results of temperature, and our choice fell with the second grid, as well as it was found that the grid of 600,000 hexahedral nodes is sufficient to maintain a balance between accuracy and computational cost, and to capture all variables that obtain in the physical domain. Here it can be seen that the mesh is very fine near the wall and around the trapezoidal groove to capture capture the flow behavior in these areas. After the calculation, let's move on the next topic, result and discussion. In order to get accurate results, the validation of this turbulence model SST Kami Omega was performed for turbulent flow field in grooved rotor. So figure 8 shows the variation of the temperature compared with those published by the experimental study. It should be mentioned here that temperature that rise along the rotor wall. Therefore, the result obtained by using ICIS fluent calculation code show a good result agreement. To see the effect of mounting different geometric shape of the rotor grooves, I plotted the temperature curves of each form. So figure 9 gives the temperature variation along the rotor wall for 3 groove shapes. The first shape is trapezoidal form with small base b equal 10 mm, and the second is rectangular shape with base equal b is 20 mm, and the last shape is trapezoidal with base equal 30 mm. So the same evolution behavior is observed for the grooved rotor at the same rotation speed, and the configuration of groove with B equal 10 mm provide better cooling of the rotor wall. Moreover, the surface temperature of the grooves with small base B equal 10 mm is reduced by of about 3 degrees because it can be seen here a difference of about 3 degrees Celsius between temperature profile due to the perturbation of the flow inside the grooves. Secondly, I plotted the Nusselt number, where the Nusselt number has greater interest in engineering application, which is used to evaluate the heat transfer rate in the groove rotor channel. So this figure shows that profiles are characterized by peaks due to a good transfer on the groove walls, and the maximum values are located at the inlet of the groove and start to decrease rapidly. As can also be seen in this figure, that in the case of groove mounted on the rotor base and the rotor with base B equal 10 mm, the Nusselt number raised by about 15% indicating good heat transfer, and is the most favorable configuration where the heat exchange in this form is more important than the others. For the thermal behavior, for the thermal effect, the effect of different shapes of the groove on the temperature distribution is observed in these contours, where the results obtained reflect the positive effect of inserting axial grooves on the rotor. Here, temperature rise in the inner rotor wall is caused by the friction during the rotation of the rotor, and the temperature contour shows also presence of instabilities due to the presence of these grooves. So, at the same axial flow, the temperature decreases near the rotor wall by decreasing the base of the groove. Thus, the trapezoidal groove with base BB equal 10 mm improves the heat exchange because the creation of vortices within the channel gives an effective cooling against to the other configuration. For dynamic effect, here the velocity contour shows the presence of contra-rotating vortices inside each grooved rotor. For the three configurations, whatever of injection velocity and rotational speed, there is the presence of recirculation zones and thus better heat transfer, especially in the case of the trapezoidal shape be equal 10 millimeter. It can be seen be seen two vortices inside the groove with height velocity. This indicates better cooling compared to the other cases. Finally, let me sum up the main idea. The result of the present numerical simulation lead to the following main conclusions. First, the SST turbulence model is utilized to investigate the effect of the groove's configuration on heat transfer improvement inside a grooved air gap of a rotor-stator system. Second idea, by comparing the evolution of the axial temperature, the configuration of trapezoidal grooves with base B equal 10 mm represents a significant decrease in the axial direction compared with the other. And the results indicate that the trapezoidal shape with the smaller base B equal 10 mm is interesting from the thermal point of view and produces the highest Nusselt number by about 50% compared to the other configuration with a bigger base. So in this case, the configuration of the trapezoidal grooves with small base presents a better thermal and dynamic optimization and achieves a good compromise between the temperature gain with maximum Nusselt number for all users, researchers and manufacturers. And thank you for your attention.